Okay, I will talk about superradiant emission from color centers in diamond. And I chose that especially because this is a collaboration with Kay and Bill, who helped us with the theory of this whole thing. Nevertheless, this is kind of the last part of my talk, the superradiance. So first, I give you more or less a little bit an overview. Strong coupling of NV defects to a superconducting resonator, what we have done in this part, talk about that. And then I show you the, let's say, 3 highlights of the past. First, a 3D lumped resonator that we discovered by accident. So it's new resonator. So it's new technology that allows us to do new experiments, and the 2 new experiments are a very simple one, relaxation time measurements of the NV defect, and then superradiance, which is a more complicated quantum mechanical effect. Okay, to start out, if you talk about resonators, we have this all already seen in Shabir's talk. So we talk about resonators not in the sense of optical resonators where you have 2 mirrors and a standing light beam in between. Our resonators are completely different in the sense that there are transmission lines. So it's basically a coaxial cable that you cut. And then by making 2 cuts, you actually have typically here the first lambda half resonance. So it's not many lambda halves like in a Fabry-Perry resonator, but just usually 1 lambda half. And then it's squeezed into this structure. And this has dramatic consequences. So first of all, let's look at typical numbers. So the typical frequency that we talk here, and that's matched to the NV center, it's about 3 gigahertz. So which makes the length, lambda half, about 30 millimeters. And what's important is the width here is completely not depending on the wavelength. So the wavelength is about 60 millimeter, but this is independent of the wavelength, totally in contrast to what we have here in transmission line resonators. So you can make that typically in our structure is about 10 microns, and which basically is limited by the lithography. And then if you look at typical numbers, a single photon at this energy, and would also like to connect to the previous talk, it's really like a single photon energy that's about 5 orders of magnitude smaller than an optical photon. So the photon that comes out of this laser that I have in my hand. So it's about 10 to the minus 24 joules. But if you calculate in the electromagnetic fields to that, you get fields of about 0.1 volt per meter and about 40 microgauss. So this means basically, if you look at these numbers, so this is a microscopic number. And these are macroscopic numbers. 0.1 volt per meter, in principle, you could measure that with your multimeter. Only in principle. But these are macroscopic numbers for a tiny amount of energy. And the reason is because we have squeezed in the electromagnetic modes between these 2 gaps. So we really squeeze it in here. And as I said, so typically these structures are superconducting. So the largest Q that we have measured at the single photon level in Vienna is about 140,000, but you can crank up to 1 million or higher. And if you look at this structure, this is basically the kind of the building block of all these superconducting quantum computer effects like IBM or Google, Rigetti, and all the others are trying. So this is the pioneering paper that we've done at Yale when I was a postdoc. Okay. Okay, and in principle, the whole thing then goes to the field of circuit QED. And what we do is typically we measure that at low temperatures. You do that in a dilution refrigerator, and the reason for that is actually not that this stuff becomes superconducting, but it's mostly because you don't want to have this resonator occupied by thermal photons. So if you look, 3 gigahertz is about 145 millikelvin. In order to be low in the, let's say, no photon occupation limit, you have to be lower than the 45 millikelvin, which is, let's say, that's a disadvantage of microwaves compared to optical photons. And then the experiments are schematically are super simple. If you want to understand the experiments, it's just a transmission experiment. So we send a signal from the side and look what's coming out here. And typically this actually is still here with a superconducting qubit, so it's this one of this transmission, transmon qubits that we have here. Today I'm going to talk about another kind of two-level system, or it's actually a three-level system, or even more. It's the so-called NV centers. So if you look at defects in diamonds, there is about 600 color centers known, and it's basically optical spectroscopy to determine where your diamond is from. And this one is a very special one. It's basically a missing carbon atom, so you have a hole next to a nitrogen replacing a carbon site here. So, and typically you see also it's called NV minus, typically there's an extra electron involved. And then if you count, you have 6 electrons in this system, so you can count there's basically 2 left over from the nitrogen, 1, 2, 3 dangling bonds from these neighboring carbon sites here, and these extra ones, which makes 6 electrons. And then you start up filling levels, like you do that in an atom or in a molecule, and then you find out that actually the ground state is a so-called spin triplet state, so it's a spin 1 state. Down here, it's like that. So it's a triplet state like this, and there is additionally this triplet state is also split up. The reason is just because there is an interaction between the 2 electrons. So the system, 2 electrons prefer anti-alignment, like this. So this state, the 0 state, has actually a lower energy than the plus or the minus state, like that. And this energy, or this splitting up, is about 2.8 gigahertz. And if you have worked with this transmission line resonator, it's straightforward to think of actually just taking a diamond and coupling it to this transmission line resonator. Good, so the idea is to recouple that. Nevertheless, I have to also emphasize most of the work in NV centers is actually done on optical transitions. So like that. So typically the experiment, or one of the cool features is actually that you can actually, with an optical scheme via this intermediate state, polarize this spin. So that it also works at room temperature. Nevertheless, we do everything at 20 millikelvin, or let's say 50 millikelvin, because this corresponds to about 140 millikelvin. Okay, and then the system is described with this rather simple Hamiltonian, even simple on the sense for an experimentalist. Okay, and this is how the system looks in general. You have a diamond and just place it on top of that. So you don't have to do any kind of complicated trapping like that, yeah. Okay, this is how the sample looks in real. What you see here is a copper box that's gold-plated. There's a PCB inside, and then there's a chip. So this shiny object is actually a sapphire chip with niobium top. Niobium is a good superconductor. And you can see, maybe, at least I can see it from here, because this is a really excellent projector. You can see the structures. You see this transmission line structure, and then it actually winds 3 times underneath this black object. And this black thing is actually a diamond. And that's just how let's say the coupling, we do the coupling. The reason this diamond is black is the following. If you calculate a single NV center coupling to this transmission line resonator, you get a coupling of about 10 hertz. Now 10 hertz is really large if you think it's a single spin. It's a single spin just coupling with a magnetic moment to an electromagnetic wave. That's super large. Nevertheless, if you look then at what you can do with that, it's not enough. So what we do is we just crank it up by n, so we take many, and we go to so-called Davis-Cummings physics. We use Dickey states, and then you get an effective enhancement of your coupling rate with g times squared of n. And typically n is about 10 to the 12th, so we go from hertz to megahertz coupling strength. What we do is, and the reason this thing is black, so we want a diamond that has a lot of these NV centers. So what we do is we take a diamond that's actually yellow, so that has a lot of nitrogen in it, and we just place it for 36 hours in the reactor. There's nothing nuclear going on, it's just shooting holes into that piece of material. So you really punch holes into this machine, and then we actually reach out to about 40 ppm NV centers. So out of the 200 ppm nitrogen. So this diamond then turns from yellow to black, and the reason it's black, it also has a lot of other defects. So neutrons are definitely not the best idea. At the moment now we're getting diamonds from Japan, or from Germany. And they're all electron irradiated, which is a much better method. Nevertheless, we have the really like a nice proof that we have here a lot of these NV centers. So this is this black piece of material placed underneath a white illumination. So we just shine white light and it's glowing back in red. And if you look back to the scheme, this is just exciting somewhere up here, going back, and then it fluoresces in the red. You can really see that live, that you have a lot of these defects. Okay, and then if you couple it to that, it's super simple. You just make a resonator, transmission line resonator that's slightly below this resonance. So typically this one is at 2.72 gigahertz, and we have 2.88 gigahertz for this magnetic resonance of the NV center, and then you apply the magnetic field. So we apply a magnetic field here and tune it. So if you make a cut here, you just see these peaks. This is just the resonator itself. And then as you tune it, you see the minus state here coming down like this, and then you see a nice avoider crossing. And yeah, okay. And if you're interested, this is the paper. And as I said, this is about 10 to the 12, which makes here from a 10 hertz coupling on the order of 10 hertz to a megahertz coupling that you see here with this splitting. Just briefly flash two experiments that we have done with that. One thing is actually we have looked at the, let's say, I just flashed that cavity protection effect. So this is an effect if you have an NV center, so you have inhomogeneous broadening. I mean, the NV centers are just different. Every site sees a different environment. It's a solid and it's a dirty system. You have a lot of it. Nevertheless, you get actually a inhomogeneous line broadening that's quite low for, let's say, a defect in a diamond. And then there is a way actually, which is coming from quantum optics, so you have a strong coupling and a non-Lorentzian line width, and that actually leads to an improved. So basically this plot is showing that the stronger you can couple these two systems, the better it becomes. You can make a mega couple. And then you can actually push that on and go to this system where you can actually burn a hole into this system. This would, initially we intended to just improve this effect, but then we realized that we have done a different system. It's actually split up. So where you get here an upper half of the ensemble and a lower half of the ensemble, and you get a nearly dark state, and you can see that you can nearly by 10-fold improve the coherence time by this trick. And I like this because this is basically now kind of an experiment on a hybrid system, and this coherence or this oscillation, the decay of this oscillation is actually better than the subparts. So it's living up to this promise that we have put into the first proposal, saying something like take system A and take system B, couple them to each other, and get out a system that profits from the two parts. And basically showing you, and this system is now even better than the two subparts. Okay, nevertheless, if you're interested, here are the two references. But today I want to, and also what we can do is with a, let's say, a longer transmission line resonator, you can couple two diamonds. You can really lead to a coupling between these two diamonds that's mediated by the transmission line here. Or you can do actually nonlinear classical physics, looking at bistability effects that we have done in this work. Okay, but one of the things then that we realized where these transmission line resonators are not ideal is the following. If you look at the crosscut to such a transmission line resonator, you have here, as I said, that the idea of it is that you squeeze the electromagnetic field into these gaps. So what you have here is a really concentration of the field of the magnetic field in this structure here, and then if you place a diamond on top of it, you have a really strong coupling to a diamond or an NV center defect that's placed around here at the surface. And nevertheless, if you have a look at the different one that's up here, the higher up you go, you couple much less. So what you get here is now an extremely inhomogeneous coupling in this system. This is no problem for, let's say, these kind of experiments that we have done here, because this is all Dickey physics. So the Dickey state, basically you can write a modified Dickey state for this kind of physics here, and you just make a weighted wave function, and you get actually, for these kind of things, it's basically working, because also you have, you go in the very low excitation manifold. However, for example, if you would like to do a pi pulse on the whole ensemble, this is completely screwed up, because this, the center that's sitting here at the surface is rotating like crazy, while the one above is just tickling, just not changing it. So for doing more complicated pulse schemes or readouts going beyond, let's say, the Holstein-Primakov approximation, this is completely failing. So we came up with a new structure, and it was just actually kind of an accident in the lab. The idea was to make a 3D cavity, which you can get from this. So it's just a hollow space milled into this piece of material, and focus the magnetic field into the center where the diamond is. Now, it turns out when we came up with this structure, has nothing to do at all with what I just said. So this is the structure that we have made here is not a 3D cavity, it's actually just a resonator, and it's very close to the LC resonator that you learn even in high school. So LC resonator in the sense that you have a capacitance. If you look at this piece of material, so you have a flap here, and you then put on this cover, you form a capacitance to the ceiling of this cover. So that's the C, and then you need an inductor, and the inductor is kind of very strange in the sense that the inductor is just a piece of material where the current flows down here and back up again. So it's a super small inductor, but that's very fortunate for us, because in kind of an LC resonator, you always have to balance the two energies, and if you have a super small inductor, it means that the current that flows here is very large. And it creates a large magnetic field here in the gap of the structure. And another advantage is that actually the field that we create here, where we place the diamond, is extremely homogeneous, or way more homogeneous than the field that changes here by orders of magnitude. And that's just how we optimize the structure, and I'm sure it's basically not, this is not the end of the story. We improved, since we made this 2 years ago, we improved that already and changed this structure, and looks now in the lab completely different. Nevertheless, so you have a very homogeneous coupling, and you can couple to a very small sample that's basically placed in here, and with homogeneous coupling, and then you basically probe the system by 2 ports. So you have a port, you make a port underneath here, it's just a coaxial cable that ends here. This is also a very, is also advantage, because you can change that in the experiment. It's not changeable in situ. Nevertheless, if we had made this chips made on sapphire, we would have to go back to the clean room, start the fabrication process, make a new clean. This one you can just screw out, cut it off, take a new one that's longer, and change and play with that if you don't like it. It's not, maybe, well, in principle we could make a motor that squeezes it in and out, and then you can change it in the experiment while it's cold. But turns out for an experimentalist this is also a very good thing. Okay, and then the quality factor, what we have reached here is about 2,000. For, let's say, the million that we had before, that's not very exciting. The reason for that, this is copper. So this is just ordinary copper from the workshop. And if you look at the residual resistance that this has at 20 millikelvin, this explains very well this Q number that we have. So from the simulation, we get exactly the same number out. It's just because the current flows in this piece of copper here or in the ceiling on top and creates a resistance, and that's limiting our Q. This is, let's say, the first measurement that we have done here. So this is without the, let's say, the NV centers tuned. So this is just a very nice Lorentzian line shape that's for this resonance. And then we can, with the magnetic field, again, we can play with the magnetic field and then tune it into each other. And you can see you have a really nice avoider crossing with a large, let's say, 12 megahertz splitting here, or twice 12 megahertz splitting, and then cooperativity of about 27 that you can see here. Really nice avoider crossing. Okay, and as I said, one of the features is if you look at the magnetic field changes here, this is about the size of the diamond, and it's about 1% change here on the typical size where we place the diamond. So we typically place it around here, such that we have just 1% of coupling strength change in the system. Okay, so this is a new resonator. Also have to say, so I should mention that you can also make it superconducting, the resonators. You can avoid the thing. This is just made out, this is just the first try. If you look at the circuit QED community, they use all kinds of fancy, very clean, non-magnetic aluminum. This is just the standard aluminum from the workshop. It showed a Q of about 500,000. Actually, this is a low number. This is already up to a million now. Just normal aluminum here, if you make it like that. So this really shows that the limiting factor was the copper, the material. Now, if you do it here in aluminum, as I said, the disadvantage here, I have to emphasize, is we cannot apply magnetic field anymore. So we cannot tune the NV centers with this system, like this. Okay, and but that's not such a big disadvantage. The reason is the following. What we do now is we place the diamond in here between these two flaps. This is a superconducting aluminum resonator. And we go to the so-called dispersive regime of cavity QED. So the resonator is slightly higher. So this one was about 3 gigahertz. And this is just machining and pushing and pulling on this. So you can yank on these flaps and then change the frequency as you want. The spins, as I said, are about 2.88 gigahertz. Now, the nice thing about the dispersive regime is, in principle, I really heard people when we started that at Yale doing experiments on that, people said, yeah, well, the resonator is bad because out of the resonance frequency itself, you don't see anything, you're blind, because you're just sensitive. And that's not true. The reason is, okay, we are, let's say, the detuning between resonance, resonator and spins is larger than the coupling strength. So from, let's say, just an avoider crossing, you wouldn't see anymore. But if you look what's left over in the Hamiltonian, it's actually very advantageous. It's in the sense that the coupling term looks like now G squared over delta. Delta is the detuning. G squared, G is the, let's say, the effective coupling strength, and times a term that goes like SZ, so the operator of the spin in Z directions times A dagger A. So it somehow looks like a change of frequency. So this is the original resonator frequency, change of this frequency that's depending on the SZ operator. So depending what the spins do, we get a small, tiny change of the resonator frequency. You let's say, the classical analog of that is basically you have a Faraday resonator, and you put some glass into a piece of glass into this system. So you changed it. But it's classical in terms of glass there or not there. This would be the state of the spinning. And the nice thing about this is it's a so-called quantum non-demolition measurement. So it's usually in the literature it's non-destructive, but I would say least destructive in the quantum sense. So it's an ideal quantum measurement. Okay, so we use that actually for a very simple measurement, and the idea is just to measure the T1, so the relaxation time of the spins that's in here. You have to read this panel actually from the right-hand side. What we do is we start out with a sample at so-called high temperature. High temperature in our sense is 2 Kelvin and higher. So 2 Kelvin basically means for the NV center spins, they're completely in a thermal equilibrium. So they're completely mixed in a mixed state. So because they couple to the bath and so on. And then what we do is we crank down the temperature of our fridge. So with the bath, we actually go to a low temperature, but the spins are still in a mixture. And then we just watch what's happening, how long it takes for the spins to go actually down to the ground state, because now they couple to a very cold bath. And the nice thing about this dispersive regime is we can really watch that. So as I said, basically we measure the frequency of the resonator, and it gives us information on SC or SC squared for the NV center. That's just technical detail because it's a 3-level system and not a 2-level system. Okay, and then you can just measure it. So we start out with a certain temperature, ramp it down, and just watch it going to a certain temperature, to a certain spin state like that. And you can see here, this is a really nice exponential, let's say, decay to the ground state here, or to the lower, let's say, lower mixed states at different temperatures. And yeah, as I said, the advantage of this dispersive measurement is we can really this is a single measurement, so we can just scale the trace. So if you do the normal measurement where you have this optical regime, you basically would make a new measurement. Can you tell them that I'm not here? Okay, so this is really this is just one measurement continuously here. With the conventional way where you have an optical detection, you would need to repeat your experiment each time. So you would need to wait until here, measure this dot, repeat the experiment, and so on. And here we just can follow that. The other thing I have to emphasize is really the time scale. So this is really hours. So when we saw that, we actually scratched our head and thought, well, what are we actually doing here? And the nice thing is that we actually turned over to people, to the community that's kind of distinct from our quantum community. It's so-called DFT calculations. So the nice thing is we collaborated with Johannes Majer, Norbert Mauser, and Peter Mohn, who are DFT specialists. And they make basically an ab initio calculation. And what they predicted, so there's no input parameter from our side, they just predicted they looked at different mechanisms, how this thing can happen, and it's basically just a coupling of the, let's say, the spin directly to the phonons that are left over. And the nice thing is that the diamond is so hard, it basically doesn't have any phonons at low temperatures, so you can just, that's why this kind of relaxation is extremely reduced. And then you can see we have here different diamonds from different systems. For example, the first one was the black one I showed you before. That was done in Vienna. And then we had some electron irradiated samples from Bologna. But the best one, let's say the purple ones, came from Japan, which are, let's say, electron irradiated samples that with really precaution that are super. And this one just really fits the 8 hours that we predict here. So this is really the first measurement of the spin lifetime of NV centers below temperatures, let's say, where this is in transition frequencies. So this is about here, 145 millikelvin. So we're below that, and it's really 8 hours. So it's super long T1 time for the system. So the kind of the critique came from my PhD students themselves. They said, so what can we do with that? It's basically, I told them, it's never going to be a problem for this system. That's the message. Okay, with that brings me to the last part, which is Superradiance. The idea is now that we go here to a system as I said, the first few experiments that I kind of skipped over were all done in this very low excitation regime. So we basically here work with decay states that have look quite bosonic, and that's why inhomogeneous broadening couldn't affect us. So the next thing that we go actually up here is really like to a total inversion or a nearly total inversion, and then look what's happening with this system. And the prediction is, it's actually quite old, and Serge Roche worked quite low for that time. If you look at the system of decaying emitters, and if you have them far spread out, you just see an exponential decay. So basically this means every NV center would decay by themselves, and that's really like just what we measured here, right? So these are far out, coupled weakly, and and that's why you get basically an exponential decay with 8 hours here. Now, if you pack them into, let's say, 1/2 of a wavelength, you get a totally different decay, which works here, which is basically enhanced by these collective states by square root n. So you get a super enhanced relaxation rate here, or coupling between the two states, which experimentally would show up as not an exponential decay, but as a kind of a burst. So that's a superradiant burst. Basically, they all start to decay collectively like this, and this is a much shorter time scale. So in order to measure that, what we did changed from the experiment. We put it actually into this cavity and coupled it directly to the field, still with, let's say, a weak coupling. The reason for a weak, let's say, coupling, let's say it's not a weak coupling. We made basically the cavity artificially bad by coupling here, by the coupling to the environment. The reason for that, we call that regime the so-called fast cavity regime, in order to distinct it from the bad cavity regime. So bad cavity basically means you lose photons out of the cavity, but to an unknown way, while here in a fast cavity, it's basically also a bad cavity, but fast cavity means you lose it out of the system to the port that you actually measure, which is here to detect. So it's a fast, that's why it's fast cavity. And if you do that and measure it here, so this is the pulse time, and we apply a pulse here, and with different rotation, with different power or amplitude. And what you can see here, which is basically here, there's an extra peak coming, and which is basically after a few hundred nanoseconds. So just imagine the scale. Before we had hours of decay, now we have here something coming out on the nanosecond scale. And that's starting to happen on the, let's say, where we have really like a pi flip of the system. And and also I have to emphasize that what we did is we also checked it with an optical detection system. So we put an optical fiber into the fridge in order to detect photons, detect the state in a different way, to actually basically confirm that we have really here a pi flip of our system. Okay, and in order to, let's say, make sure that this is really superradiance, what we did we measured it as a function of, let's say, number of emitters. The prediction here from this is basically that pulse here the pulse height should be about n squared as a function of emitters. So if you do this experiment, the nice thing about the NV centers is that these defects basically look in different directions, and by the magnetic field we can really tune different amounts of NV centers into the resonator itself. So we started out with about n, so we can really like take a quarter, 1/2, 3/4, or all of the spins that we have here. And then we do that experiment, and you can see here the superradiant burst here, and then we look just at the peak height here and plot that as a function of the number. Now the prediction from, let's say, from the classical superradiance scheme would be squared, what we get out is about a power of 1.5. Now, this is not, so what it is definitely, it's different than just a linear scaling. So it's definitely not a linear effect. So it has to be, let's say, it has to do something with superradiance. And what we learned from, especially with the help of Bill and Kay, was that when we do simulations, that this power of 1.5 is explained by inhomogeneous broadening and defects of our system. So it's just non-ideality. Nevertheless, we have a let's say, non-linear scaling of that. We can clearly see there's something non-linear going on. At least it has to. Okay, with that, I would like to summarize. I've talked about, the first part was about strong coupling of NV sectors to a resonate. So I swept over that. If you want to learn more about that, talk to me. Then I talked about these new resonators, these 3D lumped resonators that have this kind of shape like that and are fabricated in the machine shop instead of a clean room. With that, we made two new experiments. The first one was this kind of relaxation time measurement, super simple. So we take a superconducting version of that and look at the decay. The story is here, it's really like 8 hours. And the reason for that is the time is so super hard. That's why you get these low relaxation times. And yeah, so basically it takes 1 hour to one spin to flip in these 8 hours. And the last part was let's say, non-linear optics with the superradiance effect showing clearly, let's say, a common effect and superradiance. And with that, before I finish, I would like to thank actually the people that have done that, especially Andreas, who has done the non-linear bistability and the superradiance things, and Tom, who has done the relaxation time measurement. And with that, thank you for listening.
Questions? No one has any questions at all? I mean, I can ask many, but...
Cool. Simon.
So just a simple question, but you mentioned you get a slight shift in the cavity frequency when you get this when you're in this dispersive regime. Mm-hmm. What kinds of shifts are you seeing, and how strongly do you have to probe to observe them?
Oh, okay. I have to look it up. I don't have the number on top of my head, how much it shifts. Basically, the big advantage of measuring a resonator is... So what was really like, I made this mistake before. If you have a Lorentzian line curve here, I always thought you can measure, basically detect the Lorentzian line curve on the size of, let's say, the width. But the good thing is, this is such a well-defined curve that you can measure that and probe it to frequency shifts that are way sub the line width. It's because, yeah, it's a clear Lorentzian, you fit that and you get an error that's super small. Typically, we have here a line shifts that are on the order of kilohertz on a megahertz, let's say, megahertz wide transition. And yeah. And the second part was, okay, you have to be careful to probe it in the low excitation limit, because this kind of excitation, expansion here is only valid if you have on the order of if you have a low photon number in the cavity. The advantage is low means here compared to the number of spins. We don't need to be in a single photon level, but less photons than spins in the system. Because n is so large, this is still not a big limitation.
Okay, so that doesn't interfere with the conclusion you drew later about the measurements about the ensemble polarization being faster than you would typically be able to do.
Actually, I'm not sure if I...
You showed a graph with a number of decaying lines, and you mentioned that you were able to do that measurement faster than than would otherwise be the case? Yeah, this one.
Yeah.
And so that it doesn't interfere with that at all, that you have to have small...
Well, as I said, I mean, we have tried it actually not on this experiment, but we have tried it before. If you crank up your measurement power, this is not going to be exponential anymore. It's going to decay faster than exponential. Because higher terms than this, let's say, first order expansion come into play, and things like that. But you can do that and you see that you screw up your measurement. But because we are still in this low regime, you can really like go and measure and just measure this shift all over. If you make that, if you probe that weekly, you just can continuously do that. You can imagine this measurement takes, I mean, until you're really sure that you're in the ground state here, we're talking about 10 hours. And if you have to repeat a 10-hour measurement for each point, this is horror. This is already horror enough that you measure here different lines. You can imagine this is all 1 day of measurement, one line itself. But if you would have to do that in a conventional measurement where you really like make, let's say, destructive measurement in the conventional NV-center optical regime, then you completely destroy the system and you would need to start over again. Wait this time and measure this point. But we can measure here a full line, which is for the experimentalist the difference between doing the experiment and not.
Thank you.
I think they want to report.
I just want to go back to the very, very beginning when you just told us that the coupling with a single NV center is 10 Hertz.
Mm-hmm.
So I wonder if after all this journey and all the things that you have learned, you think that someday you can really do single NV center coupled with to a single NV center, because that would be exciting.
I always poke my PhD student. Actually, the last one I poked was doing his defense. And his answer was no. One thing that so the first question, the first answer is we definitely would like to go to lower ensembles, because for the Superradiance, it's still a matter how much power you have to pump in and things like that. So the next experiments, actually this was the stuff that we published. In the meantime, we have measured much better stuff with much smaller samples. However, we think to go to, with the next structures, to go about to 1,000 spins, which is not 10 to the, now we're coupling actually to many mores, which is more like 10 to the 16. So 1,000 and 10 to the 16 are different numbers, right? Nevertheless, going to a single one is going to be super hard. I would really like to do the measurement, but I don't have a real answer how to do that yet. So one thing I can answer, what we're definitely trying is we have now transmission line, kind of this style of resonators, so not transmission line, but lumped element circuits that where we go in with a focused ion beam and make a very narrow superconducting wire in this system. And try to push there something. I mean, the whole fabrication is going to be not so nice. Yeah.
Any further questions? I've got to ask, so, I mean, given where you are now, what's, Viennese time. So what's next? So I mean, so what's the plan going forward with this? I mean, what's the ultimate goal now? You've shown a whole lot of nonlinear phenomena. You understand your NV system very nicely.
One thing we would like to detect is with this system, let's say with the Superradiance, is actually not a single spin, but a single photon. So the idea is to, here, Superradiance, basically making an inverted ensemble and trigger the whole Superradiance with a single photon. That's basically one thing you can do with that. And as we heard from Javier, that in microwave physics, the single photon detector is completely missing.